So I'd like for this video to serve as something of a consolidation for several things that I've learned regarding calculus. And this video in particular is going to go from limits all the way to about implicit differentiation, ranging to about, I want to say 80 to 100 problems. And we want to essentially structure this video in a way that we're reviewing the material, but we're also practicing problems as we review. So each section that we'll do here will essentially start with a brief overview of what that concept is about, as far as I understand it. And then we'll sort of seal the deal with a bunch of practice problems. So the first thing that we usually cover is limits. So this idea of a limit. So you've probably seen the limit comprised in a notation that is like this. So what is the limit as x approaches a of f of x? Or you could say the limit as x approaches a of f of x is equal to L, where L is the limit, right? So the basic idea, and I think the best way to go about this is if you think of an x and y, if you think of a coordinate plane, and you think of a particular function, and a is just a random x value on the x-axis. The limit is concerned with trying to figure out what the corresponding y values are approaching as we approach a. And I know that sounds like a lot, but the idea is that at this point we have a y value, right? It could be anything. And at this point we have a y value, and we have y values on both sides of a. So the basic idea here is to essentially judge, as we plug in x values around a and we get corresponding y values, what are those corresponding y values approaching? So as we get closer and closer and closer, as the x values approach a, what are the corresponding y values approaching? Well, they're going to approach whatever is f of a, correct? They're going to approach whatever is f of a. And that is essentially the limit. Now, not always, right? Not always. And we'll get into more as to why that's not the case. But the basic idea here, if you think about like a real example, if we had a function, and then we had, let's say, a value of 2 here, and let's say a value of 3 and a value of 1. So the basic idea, if we ask, well, what's the limit, and let's say that the corresponding y value here is let's say 4, right? So we ask ourselves, what is the limit as x approaches 2 of f of x equal to? And what we're essentially doing in this case is we're asking ourselves, okay, as our x values get closer and closer to 2, and we plug in those x values, what are our y values getting closer to? Well, they seem to be getting closer and closer and closer to 4. Now, so that's the basic idea. It's an observation to judge what the corresponding y values yield as we essentially plug x values that are closer and closer to a as we approach a from both sides. Now, there is another thing that I'd like to make clear here, that if we had the same thing going on that we had before, but there was a hole at this point, this really wouldn't change anything. So if we said if we said in this case, the limit as x approaches a, or not a, let's actually grab a real example. If we say the limit as x approaches 2 of f of x, what is the limit in this case? Well, we're judging, what the x values approach as we put those x values into our function and get corresponding y values. We're asking what we're approaching, and from both sides, we're essentially approaching this y value of 4. So the answer here would essentially be 4. Just because there is an undefined hole at f of 2 doesn't mean that the limit cannot exist at f of 2. And we'll go ahead and make a note about that. That the limit, so I guess you could say this is our first topic, graphical limits. So we can say that the limit is concerned with what the corresponding y values are approaching as we input x values that surround a. So the limit is concerned with what the corresponding y values are approaching as we input x values that surround a. We are not concerned with what happens at f of a. So in this case, we weren't concerned with what happens if I plug in 2 into the function. We're concerned with what happens around x equals 2. So in this case, why I said the limit exists here is because it doesn't matter if this point is undefined. It doesn't matter if f of 2 is undefined. What really matters is what are we approaching at an x value of 2. So that's why I said this point here, that the limit is concerned with the corresponding y values. The limit is concerned with what the corresponding y values are approaching as we input x values that surround a. We're not concerned with what happens at f of a. We're concerned with what happens around f of a. So that's sort of the first point. And the second point is that even if f of a is undefined, you can still have a limit exist at at f of a, or you can still have a limit exist at the undefined point. That's another note there. And another thing that I will say that often comes up is that if you have a function, and actually let me put a hole in this function here. So if you have a function and let's say this is 2 and this is 4, same thing. Now, if you notice, if I plug in, if I ask you what the limit is as x approaches 2 of f of x, well, we know that the corresponding y values are approaching 4, correct? As we move closer and closer and closer to 2 from both sides, we essentially approach a corresponding y value of 4. So the limit exists, and we note that it exists at an undefined point. But now if I ask you, what's the limit as, well, not the limit, but if I ask you what is f of 2? So if I say, what is f of 2? Well, you would have to say that point is undefined, right? You'd have to say that point is undefined, because if I say f of 2, well, f of 2 is not defined, but the limit can exist at an undefined point. So if there is a hole at f of a, then f of a is undefined. So if I plug a into the function and I get a hole, then I'm going to say that f of a is undefined. So that's, but this doesn't mean that the limit cannot exist at that point. And another thing that I see quite often, and let me go ahead and load something else here. Another thing that I see quite often is something like this. So we have 3 here, we have, let's say, 4 here. So if I were to ask you, what is the limit as x approaches 3 of f of x? Well, the basic idea is that, you're asking what are the x values approaching from both sides of f of a, from both sides of a, which in this case is 3. And we can clearly see that it's approaching 4. So just because it's undefined at that point doesn't mean that the limit cannot exist at that point. So we're going to say that the limit as x approaches 3 of f of x is 4. But with that said, if I were to ask you what is f of 3, well, you plug in 3 into the function and it's an undefined point. So we're going to say that point is undefined, right? But if I change this graph, and let's say I have another point here, let's say 5, and I put a closed dot right there. Well, what that means is that f of 3 is equal to 5. So this stops being true. So the idea is you can think of it as like something of like a lane, right? You're closed in on this lane of your a value, and your limit exists at 4, but the point, if you plug in f of 3 into the function, the point is defined at 5. So the basic takeaway there is that f of a can exist at f of a does not have to, well, you could say that the limit as x approaches f of a can be different than f of a. So what I'm trying to say in this case is that the limit is 4, but f of 3 is 5, right? So the limit as x approaches 3 is 4, but if I plug 3 into the function, it's 5. So if it's defined anywhere, even if this graph was, a little more bigger than what I've drawn now, let's say like this, and it was, we had a value of, let's say, -3 here. The limit is clearly 4, but the point of f of 3 is defined at -3. So the takeaway there is that, the limit as x approaches f of a can be different than having plugged a into the function. So they don't necessarily have to correspond. And that's the basic idea. So another thing that I'm going to cover here is that is a brief overview of one-sided limits. So one-sided limits. The basic idea here is that so essentially what we've been doing so far is we're used to seeing something like this, right? And you're used to being asked something like the limit as x approaches 3 of f of x, right? This is what we're used to being asked. And what we would do is we would say, okay, well, what are the x values? If I take x values that are approaching the x value mentioned, which in this case is 3, what is my function approaching from both sides? Well, it's approaching a y value of 4, right? It's approaching a y value of 4. Just because it's undefined there doesn't mean that the limit can exist at that point. So the basic idea is now we're essentially shifting gears and we're looking at something called one-sided limits. So now if I said, okay, well, if I had something like this, and I said, what is the limit as x approaches 3 from the left of f of x, right? So now we're following the graph from the left. So we're looking at 3 and we're looking at what the y values are approaching from the left, which means we're coming from this way. And that is clearly approaching 4. But then we can extend our question and we can ask, what is the limit as x approaches 3 from the right of f of x? And in this case, we're coming from the right, so we're gonna get closer and closer to 3, the mentioned a value from the right. And we can see that our y values are essentially approaching 5, right? So the basic takeaway here is that the one-sided, we can say that one-sided limits can exist independently, correct? So it's valid for me to say, what is the limit as x approaches 3 from the left? What is the limit as x approaches 3 from the right? That's a completely valid thing to ask. But the takeaway is that if the limit as x approaches a from the left of f of x does not equal the limit as x approaches a from the right of f of x, then the limit does not exist, right? So that means that the limit does not exist. So if it's not the same from the right and if it's not the same from the left, then we say that the limit does not exist. So in this case, or not the limit, but the general limit, right? So that's an important note to say that the general limit does not exist. So in this case, I specified, I said, what is the limit as x approaches 3 from the left? Well, we said that was 4. But then I said, what is the limit as x approaches 3 from the right? Well, then we said that was 5. But if I asked you, what is the limit as x approaches 3 without specifying something in the subscript, that means I'm asking you implicitly, what is the limit from both sides? So the takeaway here is that if A does not have a subscript, that means I'm asking you what the limit is from both sides. And we can extend this and say, if the limit from the left does not match the limit from the right, then the limit does not exist. If A does not have a subscript, that means I'm asking you what the limit is from both sides. If the limit from the left does not match the limit from the right, then the limit does not exist. So just as, and so I think this is enough to be able to continue on with a problem. So the first thing that it's asking me here, and you can see that it's saying, what is the limit as x approaches -4 from the left? So we're looking for -4 on the graph, and we find that -4 is here. But instead of coming from both sides, we're instead coming from the left, because it's specified, it's specified come from the left, right? And so we're coming from the left, and we see that the corresponding y value is 1. In this case, it's asking us, what is the limit as x approaches 1 from the left? So the basic idea here is that we're coming from, so we find 1, and we're coming from the left. So that means our x values are approaching a y value of 4. And we're just coming from the left. So we found 1, and now we're coming from the left, and the x values, the corresponding y values with an input of x is approaching a y value of 4. This one says, what is the limit as x approaches 4 from the left? So now, instead of looking at -4 like we were before, we're being asked, what is the limit as x approaches 4 from the left? So this is 4, and we're coming from the left. And what we're seeing is that as our x values get closer and closer to this value of 4 from the left, they seem to be approaching positive infinity. So we're going to say that it's positive infinity. Then this one asks, what is the limit as x approaches -4 from the right? So we're looking at -4 now, and we're coming in from the right. So what we see coming in from the right is coming in from the right, and the graph surrounding this point, -4, seems to be approaching -1. So we're going to say that the limit as x approaches -4 from the right is -1. And then it asks, what is the limit as x approaches -4? So this time, it's saying the limit as x approaches -4 of f of x. It hasn't specified anything as a subscript, right? It's not saying from the right or from the left. It's just saying -4, which means this is referring to the general limit. So when the subscript is not specified, I must check what the limit is approaching from both sides. And if it doesn't match, if it doesn't approach the same thing from both sides, then I know that the limit does not exist. So I'm looking for -4, and I know that from the left it's approaching 1, and from the right it's approaching -1, which means it's not the limit from the left does not match the limit from the right. So the general limit does not exist. So I'm going to say that the limit as x approaches -4 of f of x does not exist. So whenever the subscript is not specified, make sure you check the one-sided limits, both one from the left and from the right. If they don't match, just say that it doesn't exist. This question here, the limit as x approaches 1 from the right. So we're looking at 1 and we're coming in from the right, and we see that it approaches 4. And you'll notice that before it asks us what's the limit as x approaches 1 from the left, we said that was 4. And now it's asking what is the limit as x approaches 1 from the right. We said that was 4. So that means that the limit as x approaches 1 from the left of f of x equals the limit as x approaches 1 from the right of f of x, which means that the general limit, which is the limit without the subscript, the limit as x approaches 1 of f of x, without having to specify the left or the right, because this implies both sides. So this is both sides, is what they were equal to. So this was equal to 4, which means now the limit from both sides is equal to 4. So this problem is really trying to hammer in the fact that, if it doesn't exist from both, if it doesn't exist from both sides, or if they're different from both sides, then the limit doesn't exist. But for this one, we're going to say it's 4. This one's asking the limit as x approaches 4 from the right. So this is 4, and we're coming in from the right. So you can clearly see that the corresponding y values are approaching positive infinity. And what we saw down here was it first asked us the limit as x approaches 4 from the left, which we said was infinity. And then it's asking the limit as x approaches 4 from the right, which we also said was infinity, which means the general limit without having to specify the subscript is infinity, right? Because the left and the right-hand limits both go to infinity, which means the overall limit, the general limit, must also go to infinity. So this is the next question here, and it's saying evaluate each using the graph. So we're essentially evaluating the limit by looking at the graph, the same type of question as last time. So the first question is saying, what is the limit as x approaches 2 from the left of f of x? So if you can't see this, then this is asking what is the limit as x approaches 2 from the left of f of x? So we're finding 2 on the graph, and 2 is here, and it's asking what is the limit approaching from the left? So which means we're coming from this way, correct? So the y values are essentially approaching a value of 4 from the left. So we're going to say that this one is 4. Because we found 2, and then we're coming in from the left, and we're following the graph that takes us to the left, and the y value there is 4. And don't worry about this coming in the way. Just follow the graph from the left and keep following it up. So 2 from the left is we can see, approaches 4. This one is asking the limit as x approaches 2 from the right. So if you can't see it, it's the limit as x approaches 2 from the right of f of x. And so we're trying to find 2, which we have. And we see that as we come in from the left, of 2, we are essentially approaching a y value of 2. So in this case, our y value is 2. So the limit as x approaches 2 from the left was 4, and the limit as x approaches 2 from the right was 2. And the third question asks us, what is the limit as x approaches 2 of f of x? So it's not specifying from the right or from the left. It's not telling us whether to go from the right or from the left, which means that we have to check both the left and the right hand limits. And if they don't match, then we're going to say that the limit does not exist. But if they do match, we're going to say that the limit exists at whatever they matched at. So the limit as x approaches 2 of f of x, well, we know that the limit as x approaches 2 from the left is 4, and we know that the limit as x approaches 2 from the right is 2, which means that the limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right. Therefore, we're going to say that the limit as x approaches 2, the general limit, does not exist. This question number 4 is asking us to plug in f of 2. So what do we get if we plug in f of 2? Well, You can see here that there's a closed dot here on the line of f of 2. So you can sort of, close everything else off and just look at this lane that's responsible for 2. And we see that, if there's a closed dot anywhere in that lane, then that is where f of 2 is defined. If we plug in 2 into the function, we see that f of 2 is defined at this closed dot. If there was an open dot here, we would say that f of 2 is undefined because there's no closed dot in that lane of f of 2. But since there is a closed dot, we're going to say that f of 2 is equal to 4. So if I plug in f of 2, if I plug in 2 into the function, I will get a corresponding y value of 4 because there is a closed dot in that lane of 2. And it's very important to distinguish between, what is f of 2 and what is the limit as x approaches 2 of f of x. These are two different questions. This is asking you what happens if I put 2 into the function. What do I get? This is asking you what are the y values approaching from the left and from the right of f of as x approaches 2. So these are both different questions, which is why we see them distinguished here. This one here is asking the limit as x approaches -3 of f of x. So the basic idea, so we're looking at -3 and we found -3, and we're asking what is the limit as x approaches -3. And notice how it's not specifying from the left or from the right, which means we want to essentially want to assess what the limit as x approaches -3 from the left and from the right is approaching. And if they both match, we're going to say that it is whatever that y value is that matches. And if they don't match, we're going to say that it doesn't exist. But the y value here, as we can see, is essentially approaching this y value, which is 0, right? So the basic idea is that if you have a coordinate plane and you have like a dot here, the x value there is 1. Well, not 1, but it is whatever that x value holds. But the y value there is 0. And if you have a dot here, then the x value here is 0. So if we're asked what the y value is approaching here, well, the y value here is 0 from both sides, because if we approach from this side and we approach from this side, then the y value there is 0. So we're going to say that the limit as x approaches -3 from both the left and the right is equal to 0. And we said that because it didn't tell us whether or not to look from the left or from the right, which means it's implying that we should look from the left and from the right. This one here is asking what is the limit as x approaches infinity of f of x. So essentially this is infinity and this is -infinity. So as our x values get closer and closer and closer to infinity, we see that we are approaching a vertical asymptote of -1. So I think this should be cleared up here that let me go ahead and make a note of this, that if your limit approaches negative or positive infinity, we're nearly always approaching a vertical asymptote. So just for the sake of an example, if I had something like this, right? And there was, let's say, this is +2, right? Or not a vertical asymptote, but a horizontal asymptote. Okay. So if I should probably change that. I should say a horizontal. So if I asked you, what is the limit as x approaches 2 of f of x, or not f approaches 2, but f as x approaches infinity. So what would that be equal to? So this is infinity, correct? As our x values get closer and closer and closer to infinity, we are approaching a vertical asymptote. So the value here, not a vertical asymptote, but a horizontal asymptote, right? This is a vertical asymptote. This is a I keep confusing them, but this is a horizontal asymptote. This is a vertical asymptote, right? Vertical and horizontal. But as we approach infinity, we are essentially approaching a horizontal asymptote. So as we approach infinity, we're approaching a vertical asymptote that is at 2. And if this were like -2 here, we can ask, as the limit as x approaches negative infinity of f of x, what is that? So we're looking at negative infinity and we're going this way, and we see that there is a vertical, a horizontal asymptote here at -2. So we're approaching this horizontal asymptote at -2. Okay, so that's the basic idea behind horizontal. So if our limit is approaching infinity, or negative infinity, we are nearly always approaching a horizontal asymptote, and this is true in this case as well, where we ask what is the limit as x approaches infinity. So we're going to infinity, and we see that there is a horizontal asymptote at -1. So we're going to say that it's -1. And we're going to continue this here. So we're going to say, what is the limit as x approaches negative infinity? So in this case, we're going this way. And we see that horizontal asymptote still stands. Well, actually, it would, so we want to touch graph, right? In this case, when we were going to positive infinity, we were approaching a horizontal asymptote. But in this particular case here, I guess it's, we could ask, are the x values going to infinity, or are they approaching the horizontal asymptote? Since there's a graph on the upper portion here, I'm going to say that it is approaching positive, that it's approaching negative infinity. That's what I'm going to say. And I'll check the answer for this as well. Because as we approach negative infinity, the graph seems to be going upwards to negative infinity as well. So there's that conclusion. And then the next question asks us the limit as x approaches 4 from the left. So we're finding 4, and now we're essentially approaching from the left. So we're coming in from this way, and it seems to be going down to positive infinity, right? And then we ask, what is the limit as x approaches 4 from the right? So we're coming this way, 4 from the right. And we see that we're approaching positive infinity. Here we're asked, what is f of -2? So we take -2 and we plug it into the function, and we see that it's undefined at that point. If it was a closed circle here, we would probably say that f of -2 is 2. But since it's an open circle, we're just going to say that it's undefined. Just a quick correction here that as we were saying that the limit as x approaches 4 from the left, we said that it was going to infinity, but of course down here it's negative infinity. And then the same thing as x approaches 4 generally, without specifying from the right or from the left. But if we come from the left, we know it's going to negative infinity. And if we come from the right, then we know that it is going to negative infinity as well. So both of these should essentially be negative infinity. That's the idea. So yeah. So let's take a look at another limits question here. So this one's asking us, what is the limit as x approaches 0 from the left? So as we're coming in, let me actually use red here. As we're coming in from the left, we're asking what the y value is at this point. Well, we know that if there is a dot directly on the x-axis, the y value there is 0. So we're going to say that the y value here is 0 from the left. So we're going to say that it's 0. B is asking what is the limit as x approaches 0 from the right. So we're coming in from the right, and we see that the y value here is 2. So we're going to say that's 2. And the limit as x approaches 0 generally. So since it hasn't mentioned the subscripts, whether or not to come from the left or from the right, we have to actually check both. So we have to come from the left and from the right, and then check if both of those match. If they don't match, we're going to say it doesn't exist. If it does match, we're going to say it exists at that value. So the limit as x approaches 0 from the left and from the right. Well, we know that from the left it's 0 and from the right it's 2, which means the limit as x approaches 0 from the left does not match the limit as x approaches 0 from the right. Therefore, the general limit does not exist, and we'll write DNE. The next question is asking us what is the limit as x approaches 2 from the left. So as we're coming from the left, we're asking, so this is 2 here. And as we're coming from the left, we see that our graph is essentially approaching -2. As we approach 2 from the right, so now we're coming in from this way, we see that our y value is directly on the x-axis, which means our limit there is 0. Which means the limit from the left and from the right of 2 does not match, therefore the limit does not exist of 2. So as we approach 2 from the left and from the right, the general limit, it doesn't exist because both those values don't match. This one's asking what is the limit as x approaches 4 from the left. So we're looking at 4 and we're coming in from the left. So that means, we're coming in from the left and we see that the limit is at 4. This one's asking what is the limit as x approaches 4 from the right. So we're coming in from the right, and we see that the limit as x approaches 4 from the right is also 4. Now it's asking the general limit. What is the limit as x approaches 4 from both the right and the left, because the subscripts weren't specified. If they're not specified, we check both the one-sided limits, and if they both match, we say that the y value is the limit is at that y value that matches. So we know that the limit as x approaches 4 from the left is 4, and we know that the limit as x approaches 4 from the right is 4. That means the limit as x approaches 4, the general limit must be 4. So here's another limit problem. And what we're going to do in this case is it says find each limit and the value of the function. So the first one asks, what is the limit as x approaches -1? So it's not asking us to go from the right or from the left. It's just saying, what is the limit as x approaches -1? So that means we have to check both the left and the right hand limits if it's not specifying whether to come from the left or from the right. So we find -1, and we see that the limit as we come in from the left and from the right is approaching a y value of -2. So we're going to say that the value here is -2. Then it's asking what is the limit as x approaches 1 from the right. So now we're coming from, well, let's see, 1 from the right. So we're talking about this value, not this value. It's not -1, it's 1. So we're asking what is the limit as x approaches 1 from the right, which means we're on this graph here. And just because this graph is intruding as we follow this limit from the right, that shouldn't affect anything. And we see that the value there is 3. Just follow the graph as you're coming from the right or from the left, even if there are intrusions along the way. And this one's asking what is the limit as x approaches 1 from the left. So now we're coming in from the left, and we see that the limit is at x equals 2 or y equals 2. So that means that the limit as x approaches 1 from the right is 3, and the limit as x approaches 1 from the left is 2, which means the overall limit, if I were to ask, what is the limit as x approaches 1 of f of x, you already checked the limit as x approaches 1 from the right. You said that was 3, and then you already checked the limit as x approaches 1 from the left. You said that was 2, which means both the left and the right hand limits don't match, which means the overall limit as x approaches 1 does not exist. This one's asking, what is the limit as x approaches 2? Since it hasn't mentioned whether to come from the left or from the right, we actually have to come from both sides and see if the limit exists. Or we have to see if the one-sided limits match. So we're looking at x equals 2 as x approaches 2. And we're coming in, and we essentially see that from both sides, we're approaching the same value, which is at 2. This one's asking, what is the limit as x approaches 3 from the right? So as x approaches 3 from the right, so this would be coming in from the right. And we're essentially following this graph here. And we see that the y value there is 2. Well, actually, that would have been from the left. So that means from the left, it's 2. Let's actually start this one over here. It was asking what is the limit as x approaches 3 from the right. So that means we're coming in from the right, and then the y value there is 1. And now we're coming in from the left. So we're coming in from the left, and we're following this graph, and we see that the y value there is 2. This is asking you plug in -1 into the function. Do you get a y value? So if I plug in -1, you might say, oh, I don't have a y value here, but that's not true. There's a closed dot in that lane of -1, which means that -1 is defined at I want to say like this point, which is like 2.2, 2.4, 2.6, something like that, 2.6 maybe. And then it's saying plug in 1 into the function. What do you get? So if we plug in 1 into the function, you may say that we're undefined at 1, but that's not true. On the lane of 1, there's a closed dot here, and that closed dot happens to be at a y value of 3. So we're going to say 3. Then it's asking, what is f of 3, right? So if we take 3, we plug it into the function. You may say we're undefined. You may say we're undefined, but that's not true. On the lane of 3, there's a closed dot here, which means the y value correspondingly 1.3. I don't know what the increments are here, but the y value definitely exists at, let's say, 2.4 or something. And that's the idea. Let's look at another limits problem. This one's asking, what is the limit as x approaches -2 from the left? So this is -2, and we're coming in from the left here. And we see that the y value is 1. This one's asking the limit as x approaches -2 from, this also seems to be asking as x, okay, this is asking the limit as x approaches -2 from the right. So if we're coming in from the right, we see that our graph cuts off here, so it's -2. And don't be worried that just because there's a hole here and a closed hole here, the limit can exist at the one-sided limits can exist at a closed and open hole. So that shouldn't be a matter of, that shouldn't be controversial. It can exist, the one-sided limits. So the limit as x approaches 2 from the left, we said was 1. And the limit as x approaches -2 from the right, we said was -2. This one here is saying, what is the limit as x approaches -2? So this is asking us the general limit. It hasn't specified whether to come from the left or from the right, which means we should come from both sides. So the limit as x approaches -2 from the right and from the left, well, we know what the limit is as x approaches 2 from the left. We know what the limit is as x approaches 2 from the right. Since the limits don't match, we're going to say that the limit as x approaches 2, the general limit, -2 that is, does not exist. This one's asking the limit as x approaches 1 of f of x. It's not specifying whether or not to come from the left or from the right, which means we have to check both the one-sided limits. So this is 1, the limit from the left and the limit from the right is at the same value, which is 1. So we're going to say that the limit exists. Actually, I think this is asking, yeah, the limit exists at 1. Just because there's an open hole there doesn't mean that the limit can't exist at that open hole. So the limit as x approaches -1. So this hasn't specified any subscripts for -1 or superscripts, that is. It's not asking to come from the left or from the right. So we must check both. So we're looking at -1, and from the left, it approaches -3. From the right, it approaches -3, which means the limit as x approaches -1 is -3. What is the limit as x approaches -3? Or we'll go here. What is the limit as x approaches 0? So this is 0, and as we come from the left and as we come from the right, the y value is -2. So we're going to say -2. Here, the limit as x approaches 3 from the left. So we're looking at 3 and we're coming in from the left. So that should be 5. The limit as x approaches -3 generally, we know what it's coming. We know what the limit is as x approaches 3 from the left. Now we're looking at what the limit is as x approaches 3 from the right. We know that's 5. So the limit as x approaches 3 from the left is 5, and the limit as x approaches 3 from the right is 5, which means the general limit as x approaches -3 should be the same thing that the one-sided limits are approaching if they're approaching the same value. In this case, they are approaching the same value. So we're going to say that the limit as x approaches -3, the general limit exists at 5. This is asking the limit, this is asking f of -2. So it's just asking to plug in -2 into the function. And what do we get as a result? So I'm looking at -2. This is the lane of -2. You may say that it's undefined at -2, but that's not true. There's an open hole at -2, and that there's a closed hole at -2, and that closed hole corresponds with a y value of 1. So we're going to say the y value there is 1. Then it's asking what is f of 1. So this is asking if we plug in 1 into the function, what do we get? This is 1 here. You may say that it's undefined at 1, but that's not true. On the lane of 1, we see that there's a defined hole at 1 that corresponds with 1, and that y value is at -2. Just a quick correction here. When we were looking at this limit in particular, the limit as x approaches -3, it's not asking us to go from the left or from the right. We should find -3. And we see that the limit as x approaches -3, the y value meets on this point, and the y value there is 0. So this question here is sort of dealing with limits that are approaching vertical asymptotes. So it says for the function a whose graph is shown, state the following. So this is the limit as x approaches -3. So we're looking at -3, we're coming from the left. And since the subscripts aren't mentioned, we have to essentially come from the left and from the right. So as we're coming from the left, and as we come from the right, we see that the corresponding y values are essentially approaching positive infinity from both the left and from the right. So we're going to say that the overall limit, the general limit, is positive infinity. How did I know that it's asking me for the limit from the left and from the right? Well, it's because it doesn't have a superscript. It doesn't say come from the left or come from the right. It wants me to come from both sides. This one's asking the limit as x approaches 2 from the left. So we find 2, and now we're asking what is the limit as x approaches 2 from the left? And we see that we're coming from the left, and it seems to be going to negative infinity. The limit as x approaches 2 from the right. So we're looking at 2 and we're coming from the right, and we see that it is approaching positive infinity. This one's asking what is the limit as x approaches -1. So the limit as x approaches -1, so we're finding -1, which is here. It hasn't mentioned whether to come from the left or from the right, which means it wants us to come from both sides and see if those values match. If they don't, we're going to say that the limit does not exist. If they do, we'll say that it matches, and we'll state the limit is whatever that value was that matches. So we're looking at -1. -1 is here. We're coming from the left and we're coming from the right, and we see that they're both going to negative infinity. So this question here is saying for the function f whose graph is given, state the value of each quantity if it exists. If it does not, explain why. So the first one, it says A, the limit as x approaches 1 of f of x. Since it's not specifying from the left or from the right, we're going to have to come from both sides. So we're looking at the y value of, we're looking at a y value of 1, and we see that the corresponding y value from both sides as we approach a value of 1 is in fact 2. Then it's saying the limit as x approaches 3 from the left. So we're looking at 3, and so this is 3 here. As we come from the left, you can see that we're approaching a y value of 4. So that means, well, actually that would be from the right, right? So if we're coming from the left, we should be coming from this way. So we're going to say that the limit as x approaches 3 from the left. So we're coming from this way, and we see that we're essentially approaching a value of 1. Just because it's undefined there doesn't mean the limit can't exist at that point. So we're going to say that the limit as x approaches 3 from the left, as we come from this side, corresponds with a y value of 1. This one is the limit as x approaches 3 from the right. So we're looking at 3 and we're coming from the right, which means we're on this graph here. And we're following this graph, and we see that the limit as x approaches 3 from the right is 4. This one is the limit as x approaches 3 in general. It's not asking from the left or from the right, which means that it's sort of implicitly implying that you have to check both the one-sided limits, and if the one-sided limits match, we'll say that the limit exists at that value. But we know that the limit as x approaches 3 from the left does not match the limit as x approaches 3 from the right. Therefore, the limit as x approaches 3 in general does not exist. This one's asking f of 3. So if we plug 3 into the function, what do we get? So this is 3 here. You may say that it's undefined at 3. You may say that it's undefined at 4, but that's not true. There's actually a closed dot at 3. Therefore, the y value there at that closed dot is 3. So we're going to say that this is 3. This question is asking us to sketch the graph given the following conditions. So we're going to look at our coordinate plane here. And clearly we have as x approaches -1, which means, or 1 from the left, which means that there is a x value of 1. And then as x approaches 1 from the right, so we already have a value of 1. And then it seems like we're going to have a y value of 3. So we're going to put that 3 here. And then we're going to have a value, a y value of 0, which you can put there. And then f of 1 equals 2. So which means if I plug 1 in the function, I should get 2. So that would be something like that. So the limit as x approaches 1 from the left is 3. So if I'm coming from the left, we know that I should be approaching 3, right? So as I'm coming from the left and I'm approaching 1, I should approach this value of 3 here. And then the limit as x approaches 1 from the right is 0. So if I'm approaching from the right, the y value should be 0, right? So I could say maybe something like this, right? As I approach from the right, it seems to be 0. And f of 1 is 2. So by the way, this graph here is a open circle. F of 1 is 2. So if I plug 1 into the function, I'll get a closed value of 2 there. This question here, it's asking the limit as x approaches infinity. So we're looking at, this is infinity here. So as the x values get closer and closer to infinity, what's happening? Well, it's approaching a horizontal asymptote at 0. As we go to negative infinity, we are still hugging this asymptote at 0. And then I believe, I think I cut it out of frame, but I think the other question is asking the limit, actually, it's asking the limit as x approaches 0 from the right and from the left. So as we approach 0 from the right, we see that the y value shoots up to infinity. And as we approach from the left, we see that it shoots down to negative infinity. So we'll say that the limit as x approaches 0 from the right is infinity. And then the limit as x approaches 0 from the left is negative infinity. So now we're going to start looking at solving limits algebraically. And the basic idea is that if it doesn't result in an indeterminate form, then we can essentially just plug in. So by an indeterminate form, I mean that if you plug in and you get 0 over 0, then the limit you consider does not exist. Or if you get, if you get like something over 0, then that's undefined, it doesn't exist, so on and so forth. And so if it doesn't give you those results, if it gives you a defined value, then we're fine. If not, it doesn't exist. So for this one, it's saying the limit as x approaches -1. So we can essentially just plug in -1 because it's a polynomial, it's continuous everywhere. All values are valid, can be plugged into a polynomial function. So we can say this is 2 times -1 plus 5, which is just -2 plus 5, which is just 3. For this one here, this is saying the limit as x approaches 2 of 7. So the idea here is that, I'm going to make a note of this as well, that the limit as x approaches a of a constant is the constant. So, and this is despite what a is. So it doesn't matter what a is. In this case, it was 2. The limit of a constant is just that constant. So the answer here is 7. So if I said the limit as x approaches 3 of 4, the limit is just 4. So the limit of a constant is a constant. And then for this one here, if you plug in a and you don't get an indeterminate form, then you're fine. So in this case, if we plug in a, the limit as x approaches a, the limit as a approaches 10. So we're going to essentially just plug in 10 wherever we see a. So this is a here. 3 times 2 plus a, which is 3 times 2 plus 10. And then we have 10 minus 6. So this is 3 times 12 over 4 minus, or it's equal to 36 over 4, which is just 9. Same idea. If we can plug it in without getting 0 in the denominator or 0 over 0, then we're fine. So we'll say that here we can plug in without any problems, it seems. So if we do 6 minus 2 times 3, 6 minus 2 times 3 over n squared, which is 3 squared. So 6 minus 2, so 6 minus 6 over 9 is 0 over 9. And 0 over anything is 0. Does that make sense? So it's just 0. So this is not a problem, 0 over anything. But anything over 0 is a problem. This is 5 times -2 over -2 plus 2. That's -10 over 0. So this one we'll say does not exist. This is 3 times -1 squared plus 8, which is just 3 plus 8, which is 11. This question here, there's really nothing we can do. in terms of factoring, but if we substitute 5, we get 5 minus 5 over 5 squared plus 1, which is 0 over 25 plus 1, which is 0 over 26. We're going to say that's 0 because 0 over anything is 0. In this case, we're essentially plugging in 5, and we see that that's 5 squared plus 1 over 5 minus 5, which is 26 over 0. So we're going to say that this does not exist. So for this one here, we're essentially going to plug in and see what happens. So we have 3 under root 2 times 3 squared minus 10. Which is the cube root of 2 times 9, which is 18. So 18 minus 10, which is 3 under root 8, which is just 2. So the limit as x approaches 3 of this function is 2. This question will require some algebraic manipulation. The idea here is to say, okay, well, the limit as x approaches 3, first work on simply simplifying the numerator, which is 3x, 3 minus x. So what I did here was I just multiplied the denominator, then multiplied this, and then I multiplied this. And that's what I have, and I put it over a common denominator of 3x. So I multiplied this, and I got that as a common denominator, and then I did 3 times 1, x times minus 1, which is minus x. So, and that's all over x minus 3. And what you can do at this stage is you can write this as the limit as x approaches 3 of 3 minus x over 3x multiplied by 1 over x minus 3. And what you'll notice here is that you have x minus 3 here, and you have 3 minus x here and x minus 3 here. So essentially what you can do is there is essentially this rule. And the rule is that once you're in this position of 3 minus x, x minus 3, if it's a minus b, and then on the other hand, you have b minus a, you can cancel them out and leave behind, you can essentially leave behind a negative 1. So that's the idea. You can cross these out and leave behind a negative 1. So if you have a minus b multiplied by 1 over b minus a, you can cross these out, but you'll have to leave behind a negative 1. So that's what we're going to do in this case. We're going to cross these out and leave behind a negative 1, which means we have negative 1 over 3x times 1, which is the limit as x approaches 3 of negative 1 over 3x. Now, we can plug in 3. Before, you'll notice that if we plugged in 3 into the denominator, then we would have gotten 0 in the denominator. We don't want that if we can simplify. So we plug in 3 into the denominator, and we have negative 1 over 9 as an answer. So the limit is negative 1 over 9. So this question here is essentially what it wants you to do is it wants you to use conjugate limits. But first, let's try and see if we can plug in our 0, and then maybe we'll not have to do any work. If you plug in 0, you'll get 0 plus 3, which is under root 3, minus under root 3, minus under root 3 minus under root 3 is 0. So you'll get 0 in the denominator. So you'll need to do some factoring here. Not factoring, but you'll have to multiply by the conjugate. So what we'll do in this case, we'll say x plus 3 plus under root 3. The idea is that if you have a minus b, then the conjugate of that is a plus b. And if you're not too familiar with conjugate multiplication, it would help to maybe Google what conjugate multiplication is and how it works. And we multiply top and bottom by x plus 3 plus under root 3. So we're multiplying the top and the bottom by the conjugate. And the idea behind that is once it's all said and done, the idea behind that is if you do the same thing on the top and the bottom of the numerator and the denominator, then the value of it is just 1. So you're not actually changing the value of the fraction. So what we'd like to do now is we'd only want to multiply out the thing that the part of the fraction that yielded the conjugate. So the conjugate came from the denominator. So we're going to multiply out the denominator and we'll keep the numerator the same. If the conjugate came from the numerator, we would have multiplied out the numerator and we would have kept the denominator the same. So the limit, so we'll say that the limit as x approaches 0. So the top we're keeping the same is under root x plus 3 plus under root 3. And we're multiplying out the denominator. Now, you could FOIL this as you normally would, but a key trick here is that you only have to do these terms because the middle terms actually end up canceling out. So x plus 3 times x plus 3 is just x plus 3. So when you multiply a radical with a radical, you just have what's under the radical. And then minus under root 3 times under root 3. So negative under root 3 times under root 3 is just negative 3. Well, let's see here. So it's just x plus 3. And then you do negative 3 times negative under root 3 times positive under root 3 is just negative 3. So you can see that your 3's cancel out. So the limit as x approaches 0 of x under root x plus 3 plus under root 3 is over x. And then these x's cancel out. So you're left with the limit as x approaches 0 of under root x plus 3 plus under root 3. And you'll see here now that it's safe to substitute the 0. You're not going to get a indeterminate form. We had x in the denominator, but we canceled those x's out, and this process let us do that. So now we can just substitute. We can say that this is 0 plus 3 plus under root 3. And then that's just under root 3 plus under root 3, which is 2 under root 3. The limit is 2 under root 3. This is a good example as well. We want to find the limit as x approaches negative 2 of this particular function. The problem here is that if we plug in negative 2 into the denominator right now, we're going to get negative 2 plus 2, which is 0. So we don't want 0 in the denominator if there's anything else we can do algebraically. In this case, there are things we can do algebraically. We can factor out the top, and we'll see where that gets us. So we'll say the limit as x approaches negative 2. So we'll have a negative 2 here. And then we'll factor out the numerator. So you're essentially looking for two numbers that multiply to 2 and add to negative 1 or negative x. That's just 2 and 1. But it would have to be negative 2 and plus 1. So it's just going to be x minus 2, or actually, so it would have to multiply to 2 and be positive, right? So this should be positive because it has to multiply to positive 2. If you do 2 and 1, then it multiplies to positive 2. If you do negative 2 times 1, it would multiply to negative 2. So you want it to be positive 2, so it's going to be 2 and 1. But then you notice that it should essentially also add to negative x or negative 1. So what you can do here is do something like this, where it then multiplies to positive 2. And then this would add to negative 3, so that actually wouldn't work. So as it turns out, this numerator isn't actually factorable. We can't actually factor this using real numbers. So I suppose you could just say that the limit does not exist. There's actually no way to factor the numerator. So sort of moving on to the next question here. So same approach, right? Same approach. We'll look for two numbers that multiply to 8 and add to 6. So I'm thinking about 4 and 2 because they multiply to 8 and they add to 6. So x plus 4 and then x plus 2. So we'll say that the limit as x approaches -3 is x plus 4, x plus 2 over, and it seems like we have to factor out the denominator as well. So we're looking for two numbers that add to 6 and multiply to 6. So we would want it to multiply to 6, and then we want it to add to 6 as well. And you can't really factor out the numerator because there are no numbers that add to 6 and also multiply to 6. So we'll keep that as is, and we'll try to plug what we have in. So we'll say that this is -3 plus 4 multiplied to -3 plus 2 over -3 squared plus 6 times -3 plus 6. So we would have -1 in the numerator, and then we'd have -9. Well, actually, since we're squaring -3, I suppose it would just be 9. Minus 18 plus 6. So that's -9 plus 6. What I'm starting to notice is that some of these problems aren't factorable, so it's best we actually don't touch them. So I'll actually cut these out here. And we'll sort of just move on. So for this question here, what we can do is we can say that the limit as x approaches 0, we're going to combine the numerator. So we'll say t squared plus t, and then we'll do t squared plus t minus t. So what we're doing in this case is we're combining the denominator, right? So we're saying t squared plus t, we're going to combine that, and then t squared plus t here, and then we're saying minus t. So this is sort of our first step, as it were. These t's would cancel out, so we're left with the limit as x approaches 0 of t squared over t squared plus t, and one of these would cancel out, so we'll say the limit as x approaches 0 is just t over t squared plus t. And what we'll do here is we'll say that the limit as x approaches 0, so we'll factor out a t, so t plus 1. So we'll say that the limit as x approaches 0 is 1 over t plus 1, which is 1 over 0 plus 1, which is just 1 over 1, which is just 1. That sort of concludes solving limits using algebra. And now, essentially, what we want to do is we want to look at continuity. And so this question says at which x values is the following function discontinuous? So let's go ahead and take a look here. So we want to leverage our understanding of limits in general. The basic idea is that so if we'll say that if the function is continuous at x equals a. So if the function is continuous at x equals a, then the idea is that the limit as x approaches a of f of x should equal f of a. So basically what I'm trying to say is that, if I had a function like, let's say, some random function, and this was 2 and this was 3. So if the function is continuous at x equals 2, then the limit as x approaches 2 of f of x should be equal to f of 2. So if I take the limit as x approaches 2 of f of x, and then I plug in 2 into the function, then the value that I get if I plug in 2 should equal the value that I get for the limit as x approaches 2. Remember that this sort of implies that the limit exists from both sides. So actually what you want to check is if the limit as x approaches 2 from the left of f of x is equal to the limit as x approaches 2 from the right of f of x equals f of 2. So if these three conditions equal themselves, then we'll say that the function is continuous at that value. So that's the basic idea. So when we're looking at when we're looking at problems like this, where, and let me actually rewrite it again so that it's very clear. This problem here is saying that it's saying that f of x is equal to x squared minus x squared minus 1 when x is not equal to 1, and then it's 1 when x is equal to 1. So what I'm trying to say here is that I want to check whether or not the function is continuous at a equals 1, at the value of 1. Or it's saying at which x values is the following function is continuous. I know that it's doing something weird at 1, so I want to check using algebra. So I know that my theorem tells me that the limit, as x approaches a, or in this case, my a is 1, the limit as x approaches a from the left of f of x should equal the limit as x approaches 1 from the right of f of x should equal f of 1. If these conditions equal themselves, then I'm going to say that it's continuous at 1. If not, I'm essentially going to say that it's not, right? So this is sort of my point of interest. My point of interest is 1, because I know that the function is doing something weird at 1, which is why I've chosen an a value of 1. So first let me check, is the limit as x approaches 1 from the left of f of x, right? I'm going to check what that is. So if I'm approaching 1, we can see here, if I have a value of 1, if I'm approaching 1 from the left, that means I'm coming from this way. That means all those values that are approaching from the left are not equal to 1. So when it says, so that means I want to use this function to judge what the limit is at those points. So this is saying when the x value is not 1, use this function. So I'm going to use this function because I know that if I'm coming from the left, then all those values are clearly not 1. They're everything to the left of 1. So I'm going to use this function. So I'm going to say that the limit as x approaches 1 from the left of f of x is this. The limit as x approaches 1 from the left of x squared minus x squared minus 1. Okay. Now, if I put 1, so now I'm just basically solving this problem. And if I put 1 into the denominator, I'm going to get 1 minus 1, I'm going to get 0. So I don't want that. So I'm going to factor. I'm going to factor the top. I'm going to say that this is the same thing as saying the limit as x approaches 1 from the left of x minus 1 over the difference of squares, x minus 1, x plus 1. These x minus 1's cancel out. So I'm going to say that the limit as x approaches 1 from the left is x over x plus 1. Now I can put the 1 in the denominator, and I can put 1 in the top, because this would just be 1 over 1 plus 1, which is just 1 over 2. That means the limit from the left, that means that the limit as x approaches 1 from the left is equal to 1/2. Now I want to check the limit as x approaches 1 from the right of f of x. So if I'm coming from the right, that means I'm coming from all the values that are not 1. So I'm going to choose this function, because this says if your x values are not 1, use this function. So I'm going to use this function. So I'm going to say that this is the same thing as saying the limit as x approaches 1 from the right of f of x. And as we approach from the right of f of x, I'm going to use this function. So this is the same thing as saying the limit as x approaches 1 from the right of x squared minus x over x squared minus 1. But I know if I put in 1 now, it's going to be a problem. So I'm going to have to factor. And I've already factored this down in the previous problem. So I'm going to say that this is just x over x plus 1, because that's what I got when I factored this down. I got x over x plus 1. And now I can just say that this is 1 over 1 plus 1, which is 1 over 2, which means the limit from the left and the limit from the right, they are equal, right? So the limit from the left and the limit from the right are equal, which means this and this match, they're equal. But what about f of 1? What happens if I plug in 1 into the function? Well, it says that means my x value is 1. So when I plug in x into the function, I have to say 1. So the limit as x, well, so basically what I'm trying to say for the last part is that it's asking me what is f of 1. So I'm not going to use this function, because this function is saying if your x is not equal to 1. I want to use this function, because this function is saying, is my x equal to 1? It is. It's 1. So when your x is equal to 1, your y value is 1. So the limit as x approaches 1 from the right was 1/2. The limit as x approaches 1, sorry, the limit as x approaches 1 from the left is 1/2. The limit as x approaches 1 from the right is 1/2. But f of 1 is 1, which means these all don't match. Only 2 of them match. I need all of them to match in order for this to work. So since they all don't match, I'm going to say that it's discontinuous at x equals 1. This is the same type of question where it wants me to essentially find the points at which the function is discontinuous. And for this problem here, what I essentially want to do is I want to see what my point of interest is. Where is the function acting up? It seems to be acting up at x equals 0. So my point of interest is at x equals 0. Which means that the limit as x approaches 0 from the left of f of x should equal the limit as x approaches 0 from the right of f of x. And both of these should equal f of 0. Let's see if this works. So let's first talk about the limit as x approaches 0 from the right of f of x. Well, which function should I use? If I'm looking at 0 on a graph and I'm coming from the right, that means all these values are greater than 0. So I should use this one. This one says if your values are greater than 0, then use 1 minus x squared. So I'm going to say that the limit as x approaches 0 from the right is 1 minus x squared. And what can I put my can I put 0 in without getting an indeterminate form? I sure can. So I'll substitute. I'll say 1 minus 0 squared is just 1. So that means my limit as x approaches 0 from the right is 1. Now we'll check the limit as x approaches 0 from the left of f of x. Well, which function should I use? Well, since this is saying that if your x values are less than 0, because you think about it, if I'm coming from the left, then my x values are less than 0. So if I'm coming from the left, I should use this function. So I should use the limit as x approaches 0 from the left of cosine of x. So can I substitute 0 in here without any problem? Well, I can, because the cosine of 0 is just 1. So that means the limit as x approaches 0 from the left is 1, and the limit as x approaches 0 from the right is 1, which means they both match. This is true and this is true, but let's see if the last is true. Is it all equal to f of 0? Well, if I plug, it says if your x value is 0, which now I'm trying to check what happens if my x value is 0, your answer is 0. So this came about to being 1, this came about to being 1, but this is 0, which means the function is not continuous at x equals 0. So this question is essentially asking to find the points at which the function is discontinuous. It seems to be doing something funny at the values of 1 and 4. So these are my points of interest. So I'm going to say this is my points of interest. So I have 2 points of interest. One point is at x equals 4, and another point is at x equals 1. I know this because I see that the function is doing something weird at these points. So for it to be continuous at x equals 4, the limit as x approaches 4 from the left of f of x should be equal to the limit as x approaches 4 from the right of f of x, and this should all be equal to f of 4. So first, let's check the limit as x approaches 4 from the left of f of x. Which function should I use? Well, if I'm coming from the left, if I have 4 and I'm coming from the left, that means all these values are less than 4. This one says if your values are less than, well, it says, here it says if your values are less than 4, right? It says if x is greater than 1 but less than or equal to 4. So I'm going to use 3 minus x. So I'm going to say the limit as x approaches 4 from the left of 3 minus x is equal to what? Well, let me try substituting. Can I substitute without an indeterminate form? The answer is yes. So I'll say 3 minus 4, which is negative 1. So the limit as x approaches 4 from the left is negative 1. What about the limit as x approaches 4 from the right of f of x? What should I use? So this means that all my x values are greater than 4. So if they're greater than 4, I want to use this one, right? Because it says my x values are greater than 4. I'm going to use this function, which means that the limit as x approaches 4 from the right of under root x, let me try substituting 4. I'm going to get 4, and then this is just 2. So clearly my limits from the left and the right don't match, so I'm not going to even check if it's equal to, if f of 4 is equal to that value, because, you know, it's already not continuous at f, it's already not continuous. The limits don't match the same, so it can't be continuous. So I know for a fact that it's not continuous at x equals 4. Let's see our other point of interest, which is at x equals 1. So for this to work, for it to be continuous at x equals 1, the limit as x approaches 1 from the left of f of x should be equal to the limit as x approaches 1 from the right of f of x, which should be equal to f of 1. So first, let's check the limit as x approaches 1 from the left of f of x. Which function should I use? Well, this one says that if your x values are less than 1, well, if I'm coming from the left, they have to be less than 1. Well, think about it. If I have 1 here and I'm coming from the left, that means all these values are less than 1. So this one says if your x values are less than 1, use 2 to the power x. So 2 to the power x. So I'm going to say that this is the same thing as saying the limit as x approaches 1 from the left of 2 to the power x. This is just 2 to the power 1, which is just 2. This one is the limit. So now we're going to check the right. The limit as x approaches 1 from the right of f of x is equal to the limit as x approaches 1 from the right of which function? Well, if I'm coming from the right, my values must be greater than 1. So if this one says if your x values are greater than 1, use this function. So I'm going to use 3 minus x. This is 3 minus 1, which is equal to 2, which means the limit as x approaches 1 from the right and from the left. The right and from the left are equal to 2. So my function is, so these two conditions are satisfied. Let's check the last condition. What happens if I plug in 1 into the function? This one says if your x values are less than or equal to 1. So I want to use this one. So f of 1 is essentially just 2 to the first power, which is 2. So which means my function is continuous at x equals 1, but it is not continuous at x equals 4. Let's work on another continuity problem here. Our points of interest, or just a singular point, is at x equals 1, because the function is clearly doing something odd at x equals 1. So for this to be continuous at x equals 1, for the function to be continuous at x equals 1, the limit as x approaches 1 from the right of f of x should equal the limit as x approaches 1 from the left of f of x, which should equal f of 1. So first, let's check this condition. Is the limit as x approaches 1 from the left or from the right of f of x? Which function do we use? Because if we're approaching from the right, that means all our values of x are greater than 1. So we should use ln of x. So we're using the limit as x approaches 1 of ln of x. So if I plug in 1 into the function, I get ln of 1 is actually 0, I believe. So let me go ahead and check that. Ln of 1 is 0, correct. So ln of 1 is 0. So that means the limit as x approaches 1 from the right is 0. What is the limit as x approaches 1 from the left of f of x? Well, from the left, my x values are less than 1. So this is saying that if your x values are less than 1, use this function. So that means I have to use the limit as x approaches 1 from the left of 1 minus x squared. If I substitute, I get 1 minus 1 squared, which is 1 minus 1, which is 0. Which means the limit is the limit from the right and the left match. So these two conditions are satisfied. Let's check the last condition. So what is the limit? What is the limit? Well, what is f of 1? So this says if your x values are less than or equal to 1, use this function. So that means f of 1 is equal to 1 minus 1 squared, which is 1 minus 1, which is 0. So this is 0, this is 0, and this is 0, which means that the function is continuous at x equals 1. Let's take a look at this question here. It's essentially telling me, what are my points of interest? So my points of interest are at x equals 3, right? So for this to be continuous at x equals 3, the limit as x approaches 3 from the right of f of x should equal the limit as x approaches 3 from the left of f of x, and all of this must be equal to f of 3. So let's assess. Let's check if we're right or wrong or whatnot. So first we're going to check what is the limit as x approaches 1 from the left of f of x. Well, as we approach 1 from the left, or not 1, but in this case our point of interest is 3. That means our values are less than 3. So we don't have an option to go less than 3, but we know that if our x value, so this is 3, and if we're coming from the left, all those values are values that are not 3. They're also less than 3, but this particular question does not allow us to check if they're less than 3. But we know that we can use this function here. So the limit as x approaches 3 from the left of 2x squared minus 5x minus 3 over x minus 3. If we plug in 3 now, we're going to get an indeterminate form. So we should actually factor numerator. So we essentially want to factor 2x squared minus 5x minus 3. So 2x squared minus 5x minus 3. This is negative 6x squared. We want to find two numbers that add to negative 6x squared and well, multiply to negative 6x and add to 5. That's, in my opinion, 6 and 1. But it should be negative 6x and then negative 1x. So what that would, or plus 1x, what that would do is it would add to negative 6x squared, but it would also get us to negative 5. So that's just 2x squared minus 6x minus x, or plus x, minus 3. So if I factor this out by grouping, I can say that this is 2x, x minus 3, plus 1, x minus 3. So my answer is 2x plus 1, x minus 3. So I can say that this is x minus 3, 2x plus 1, and then over x minus 3. These cancel out. So the limit as x approaches 3 from the left of 2x plus 1 is what I'm looking at. Now I can substitute. So now I can say that this is 2 times 3 plus 1, which is 6 plus 1, which is 7. So the limit as x approaches 3 from the left is 7. Not too sure what happened there. And then if I'm looking from the right, well, I'm going to have to use the same function because all those values from the right would not be equal to 3. So it's telling us to use this function. And if I do that, I'll have to factor again, and I'm going to end up substituting 3 again anyways. So it would still come out to 7, which means the limit as x approaches 3 from the left and from the right is equal to 7. But then it's asking us, you know, so essentially what I'm trying to say is that this condition is met and this condition is met. But what about this condition, right? What is f of 3? Well, it says when x is equal to 3, your value is 6. So this is 7, and this is 3, which means this is not continuous at x equals 3. Now we are concluding continuity, and we would like to transition into talking about, I think I'm going to divert to some true or false questions regarding continuity. First, we'll actually finish up on infinite limits, and then we'll divert our attention to continuity. The basic idea with limits that go to infinity is that you can sort of, there's an approach by which you can judge whether or not the function, like what the limit is, and there are some rules to do that, but I'm going to cover the algebraic approach. So for this limit, the rule is to divide by the greatest power in the denominator. The greatest power in the denominator is clearly x. So what we can say here is that this is equal to the limit as x approaches infinity of -2 over x, and then 3x plus 7 over x. And then we can say that this is equal to the limit as x approaches infinity of -2 over x divided by 3x over x plus 7 over x, which is equal to the limit as x approaches infinity of -2 over x over 3 plus 7x. This goes to 0. This goes to 0. So we're left with 0 over 3, which is 0. The basic rule to remember is that if your denominator is like, if your denominator is like a constant and you have like infinity or negative infinity in the bottom, the whole thing will go to 0 because you're dividing by greater and greater numbers in the denominator, and that would make your number smaller and smaller and smaller. and it would essentially approach 0. If it's infinity in the top and 0 in the bottom, or sorry, a constant in the bottom, then it's going to positive or negative infinity respectively, depending on, if it was going to positive or negative infinity in the first place. But that's the idea. So we divided by the x, like if it was x to the third, we would divide by x to the third because that's the greatest variable holding the greatest amount in terms of exponents. But what we did was we isolated so that we could see individually what's happening. And so we said this goes to 0, this goes to 0, this goes to 0. This goes to 0 and this goes to 0. That means we're left with 0 over 3 plus 0, which is 0 over 3, which goes to 0. But you could have determined it a little logically as well. And you could have said that, in the denominator, if we plug in increasingly large numbers, then, it's going to get really, really, really small. So you could have looked at it that way. And then we'll look at this one as well, similar to that. So what we'll do is we'll say, okay, the limit as x approaches negative infinity, we'll divide by the greatest power in the denominator, which is t to the third. So what we're essentially doing is we're dividing by 3t squared plus t over t to the third, and then t to the third minus 4t plus 1 over t to the third, which equals the limit as x approaches negative infinity of 3t squared over t to the third plus t over t to the third over t to the third over t to the third minus 4t t to the third plus 1 over t to the third, which is essentially equal to the limit as x approaches negative infinity of 3 over t plus 1 over t squared over 1 minus 4 over t squared plus 1 over t to the third. Again, this goes to 0, this goes to 0, this goes to 0, this goes to 0, which means we're left with 0 over 1, which is 0. So our answer is, in fact, going to be 0. And you should see this as well because, we have a really, really dominant t to the third in the bottom. So if we plug in a t to the third in the bottom, those numbers are going to get gradually larger. Our number will approach 0. Same idea, we'll grab the largest power in the bottom, and then we'll divide by that. So this is the limit as x approaches infinity of 3x cubed minus 8x plus 2 over x to the third divided by 4x to the third minus 5x squared minus 2, which is equal to the limit as x approaches infinity of 3x cubed over x cubed minus 8x over x cubed plus 2 over x cubed over 4x. So we want to divide the new denominator as well by x cubed. X cubed minus 5x squared over x cubed minus 2 over x cubed, which is equal to the limit as x approaches infinity of, so these would cancel out. So we're left with 3 minus 8 over x squared plus 2 over x cubed over 4 minus 5 over x minus 2 over x cubed. This would go to 0, this would go to 0, this would go to 0, this would go to 0. We're left with 3 over 4. So here, what we want to do is we want to take the biggest power in the denominator and divide by that. So that's the limit as x approaches negative infinity of, 1 plus 4x to the 6th divided by x to the third over 2 minus x cubed over x to the third, which is equal to the limit as x approaches negative infinity. So what this is going to be here is we're going to bring this inside by squaring it. So we're going to say that this is 1 plus 4x to the 6th over x to the, so this would be, if we square it, it would be x to the 6th divided by 2 over x to the 3rd minus x to the 3rd over x to the 3rd, which would be the limit as x approaches negative infinity of 1 over x to the 6th plus 4x to the 6th over x to the 6th divided by 2 over x to the 3rd minus 1, which is the limit as x approaches negative infinity of 1 over x to the 6th plus 4 over 2 over x to the 3rd minus 1. This would go to 0, this would go to 0, so we're left with under root 4 over negative 1, which is negative under root, which is negative 2. So the limit as x approaches infinity, in this case, we're going to divide the numerator and the denominator by x plus 3x squared. Or sorry, by x plus 3x squared. That's the highest one in the denominator, right? So 4x minus 1 over x is equal to the limit as x approaches infinity of x plus 3x squared over x squared over 4x over x minus 1 over x, which is equal to the limit as x approaches infinity of, so we'll say that this is x over x squared plus 3x squared over x squared over 4 minus 1 over x, which is equal to the limit as x approaches infinity of 1 over x plus 3 over 4 minus 1 over x. This goes to 0, this goes to 0. This is under root 3 over 4. Let's look at a couple true-false questions here. Can a point be continuous and defined at the same time? So can a point be continuous and defined, undefined at the same time? So think about it, right? If you're looking at a graph, right? Well, we say that this point is continuous, right? This point is continuous. But if it's undefined, we know that it must have an open circle, which means this is false. A point cannot be continuous and undefined at the same time. This one says true or false. If the limit as x approaches 2 from the left is 3, and the limit as x approaches 2 from the right, does the limit exist? So this is false, correct? Because we know that the limit as x approaches a exists if and only if the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x. Only in this circumstance can the limit exist. So in this case, the limit as x approaches 2 from the left is 3, and the limit as x approaches 2 from the right is 4. So we'll say that the limit does not exist. So this is false. The limit cannot exist. One is saying if the limit as x approaches 2 from the left is 3, and the limit as x approaches 2 from the right is 3, does this mean that f of x is continuous? So think about it. So we have this, right? 3, like a point like that. So the limit can exist at an undefined point, right? So at an undefined point, this point is not continuous. It's not continuous, but the limit can exist there, right? So it says if the limit as x approaches 2 from the left is 3 and the right is 3, does this mean that that the point is continuous there? So this, it can mean that the point is continuous. Like there's a possibility that you have a graph like this where the limit is also continuous, but it doesn't have to be the case, right? It doesn't have to be the case. You could have a point where there's an open hole and the limit exists there, and the limit from the left and the right are both the same. So the overall limit exists, but you don't necessarily have to have it be continuous. So this one is not, that's the explanation behind this one, that not in all cases does this mean that it must be continuous. So let's look at another one. So write the theorem that outlines the condition for continuity. So the theorem that outlines the condition for continuity is that f of that x equals a is continuous if the limit as x approaches a of f of x is equal, from the left, is equal to the limit as x approaches a from the right of f of x is equal to f of a. Then it is continuous. What is the limit? Explain your answer. So we said that the limit is an observation, right? It's an observation. So if you have an x value here, so the limit as x approaches a, so this is our a value. So basically the limit is a mathematical observation that we use to assess what the function is approaching as we input values of x from both sides of a, and we'd like to know the corresponding y value around a. So the basic idea is that the limit is an observation, and it allows us to judge what the y values are approaching as we get closer and closer and closer to a, or as we input values of x into the function. As we input values into the function as we approach a from both sides. So it's an observation of what we're approaching. This one says the true or false, the limit can exist at a point where the function is discontinuous. That is true. If you remember, we said that, if we had a value of a here, the limit can still exist at this point, even though it's not continuous there. So that's true. The limit can exist at a point where the function is continuous. That also is true. So both are true. The limit can exist at a point where it's discontinuous and continuous. Both cases are true. So we've talked about limits, continuity. We've talked about, let's see here. So we've looked at graphical limits, algebraic limits, continuity. We've looked at some true or false questions, and now we're moving on to the derivative. So now we're sort of transitioning from continuity onto the limit definition of the derivative. So if we're not entirely familiar, the limit definition of the derivative is basically an interpretation of the derivative with regards to limits. So what this essentially means is that if you have, so if you're looking at, so basically you could say that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. That's the limit definition of the derivative. So if someone gave me like a function, like if they said f of x equals x squared, find f prime, I could use this definition in order to get f prime. So I can say that f prime, I know that f prime equals f of x plus h minus f of x over h. So my goal is to just find out what is f of x plus h, what is f of x? So when it says f of x plus h, it's actually telling me take x plus h and plug it into x squared. And that will be my f of x plus h. So x squared. So if I take x plus h and plug it wherever I see x and x, I would essentially have x plus h squared. So this is my f of x plus h. My f of x was already given to me in the question. It's x squared. So that means f prime of x equals f of x plus h, which is x plus h squared, minus f of x, which we know is x squared, over h. We're going to have to distribute this. Well, and actually, of course, I want to mention here, it's the limit of this. It's the limit of this guy. If you remember, there's the limit in this definition, so it should be in this definition as well. It's the limit as h approaches 0 of this component here. So if I take x plus h squared, that's just equal to x plus h, so that's x squared plus xh plus xh plus h squared. That's x squared plus 2xh plus h squared. And then we can put that here. We can say that this is x squared plus 2xh plus h squared minus x squared over h. These cancel out. So we're left with the limit as h approaches 0. And again, we should have the limit sign here. We should have the limit sign, the limit as h approaches 0. We should have the limit sign there. The limit as h approaches 0 of 2xh plus h squared over h. This is the limit as h approaches 0 of, we're going to factor out an h, 2x plus h over h. These h's cancel out. So this is the limit as h approaches 0 of 2x plus h, which is 2x plus 0, which is just 2x. So the derivative of x squared using the limit definition is 2x. And of course, you could use differentiation rules to find the derivative. You could say that's just 2x, right? Same idea, same idea. And if so, so this is one type of question. It can say, you know, given f of x, find f prime of x using the limit definition. But then it could also tell you to find the equation of tangent line. So not only can it say, okay, it can say f of x equals x squared. Find the equation of the tangent line at 3, 2. So let's actually go down here and do this again, but we've twisted the question a bit. So now it's saying, f of x equals x squared. Find the equation of tangent line at x, 2, 3. Okay, so there are a number of steps that we have to take. So we know we have f of x equals x squared. We then need to find f prime of x. This is the derivative function. This is the derivative function. So once we have the derivative function, we can then plug our x value into the derivative function, f prime of the x value. And then once we have that, we can essentially then, we have m. Now, what is m? M is the slope. So m is the slope. M is the slope. So this function gives us the slope at any given value of x. And why we want the slope is because if we want to find the equation of the tangent line, we have to use this formula, y minus y1 equals mx minus x1. We have to use this formula to find the equation of the tangent line. And we know y1, y1 is just 3. we know x1 is just 2. We want to know m, right? So what is m? Well, that's what this will give you if you plug in your x value into the derivative. So y minus y1 equals m. We now know m. If we plug in, so we know that the derivative of this using the limit definition we found was 2x. So if we plug if we do f prime of 2, that's just taking f prime, which is 2x. We know that f prime is 2x. Taking f prime and then plugging 2 into f prime, which will give us m. So this is just 2 times 2, which is just 4. So 4 is the slope. So y minus y1, which we know is, so y minus y1 equals m x minus x1. So y in this case, we keep the same. Y1, we plug in our y value, which is 3, equals m. Well, what is m? It's 4. And then x minus x1, what is our x value? It's 2. So that's 2. So y minus 3 equals 4x minus 8. Y equals 4x minus 5. That's the equation of the tangent line. And we're going to see more problems like that. But just know that the general map is you're given f of x, okay? And you're given 2 points, 2, 1. If you find f prime of x, plug in this, f prime of your x value will give you m. And this m you use here, y minus y1 equals mx minus x1. And then this will give you the slope of the tangent line. Your x value goes here, your y value goes here, and your m goes here. This one's saying find the equation of the tangent line at the given point using the definition of the derivative. So let's go ahead and try to magnify this here. So we're basically piggybacking off the same idea that we had previously, which is that first we want to find the derivative of the function. So once we have the derivative function, then we're going to plug the x value into the function, and then we're going to use that as our m, and then m is going to be put in the slope formula. I mean, the m will be considered as the slope, and it will be put in the tangent line formula. And then we will be able to find the equation. So y prime, in this case, will be the limit as h approaches 0 of f of x plus h minus f of x over h. And we essentially know that f of x plus h is essentially going to be x plus h. I plug it into this function here. So that would be x plus h plus 2 over x plus h minus 3. And then we already know what f of x is. We're trying to find both of these components. So this is this component, this is this component. And f of x is x plus 2 over x minus 3. And so now we can say that this is equal to the limit as h approaches 0. We know what f of x plus h is. It's x plus h plus 2 minus f of x. Well, what is f of x? F of x is this guy. X plus 2 over x minus 3. Right. So 1 second here. We're essentially taking this and we're putting it as f of x plus h. So that's x plus h plus 2 over x plus h minus 3 subtracted from f of x, which is x plus 2 over x minus 3 all over h. Or we can say multiplied by 1 over h. now we'll just need to simplify really. So this will be x minus 3, x plus h minus 3, and x minus 3 here, x plus h plus 2 minus x plus 2. Which is the limit as h approaches 0. So now we're going to have to distribute. So we'll have x squared plus xh, x squared plus xh plus 2x minus x minus 2. And we'll keep this the same. So let's see here. We combine the denominator, multiply. You know what? Let's take a step back, because what I'm thinking is that what we should have done here is we should have combined the denominators. So we would have x minus 3, it's the limit as h approaches 0, of x minus 3 multiplied to x plus h minus 3, and multiplying these guys is x minus 3, x plus h plus 2, x minus 3, and then x plus h plus 2, minus x plus 2 multiplied by x plus h minus 3. Okay, so we multiplied these, and then we multiply these, and then we multiply these. So this will be x squared, x squared plus 2x, x squared plus 2x. Actually, it will be x squared plus hx, because essentially what's happening is we do the first terms first, x squared, then plus hx plus hx minus 2x. So x squared plus hx plus x squared plus hx plus 2x, then minus 3x minus h minus 3h minus 3x minus 3h minus 6. So x squared plus hx plus 2x minus 3x minus 3h minus 6. And then we're going to distribute the inside. X squared plus hx, x squared plus hx, x squared plus hx, so x squared and plus hx minus 3x. So x squared plus hx minus 3x. And this was inside, we had x plus 2, correct? So that would be plus 2x plus 2h minus 6 over everything we had before. So this is the limit as h approaches 0 of x squared plus hx plus 2x minus 3x minus 3h minus 6 minus x squared minus hx plus 3x minus 2x plus 2h plus 6 over everything that we had. Everything that we had before, so minus hx plus hx, x squared minus x squared minus 6 plus 6 minus 2x plus 2x minus 3x plus 3x. So we're left with the limit as h approaches 0 of minus 3h plus 2h over what we had before, which was x minus 3, x plus h minus 3 times 1 over h. This is the limit as h approaches 0 of, we're going to factor out an h, negative 3 plus 2 over everything that we have in the denominator, which is then going to be the limit as h approaches 0. These h's cancel out. We're left with negative 1 over x minus 3, x plus h minus 3. X minus 3 and then x plus h minus 3. So we could safely insert a 0 now. So we'll say negative 1 over x minus 3, x plus 0 minus 3, which is just negative 1 over x minus 3, and then x minus 3. So this is negative 1 over x minus 3 squared. This is your f prime of x. So your derivative function f prime of x is equal to negative 1 over x minus 3 squared. Now, let me just go ahead and confirm this fact. The problem that we had here was when we were multiplying this side, this should be 2h, so positive 2h on this side. And then once we open the bracket, it should then change to negative 2h. So instead of being negative 3h plus 2h, it's negative 3h minus 2h. So this is negative 3 minus 2, which becomes negative 5. So this should be negative 5 instead of negative 1. So it's instead negative 5 over x minus 3 squared. It's negative 5 over x minus 3 squared. But now what we essentially want to do in this case is that this is our derivative function, so we're going to plug in our x value to find our value of m. So we're going to say f prime of, what is our x value? In this case, our x value is 2. So f prime of 2 is equal to negative 5. Is our x value 2? Yeah, it's 2. So negative 5 over 2 minus 3 squared, which is negative 5 over negative 1 squared, which is just negative 5. So this is our m value, and let's go ahead and check in the solutions if that's what we got. So this is our m value, negative 5. And what you essentially want to do now is you want to use your m value in the point slope formula, which is y minus y1 equals m, and then x minus x1. So y minus our y value, which is negative 4. So y minus minus 4 equals m, which is negative 5, x minus our x value, which is 2. That's y plus 4 equals negative 5x plus 10, which is y equals negative 5x plus, it would be plus 6. That's the slope of our tangent line. The next question gives us it gives us f of x minus 1 over x plus 1. So let me go ahead and write that a little better. And it wants us to find, it essentially wants us to find the derivative using the limit definition. So we're going to go ahead and do that here. So the limit definition is f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. That's the limit definition. So our f of x plus h here is x plus h minus 1 over x plus h plus 1. And now that I think about it, I think we've already done this question, I think, because it was slightly similar to the previous question, but not exactly, not exactly. So our f of x we already know is x minus 1 over x plus 1. So f prime of x is going to be the limit as h approaches 0 of f of x plus h, which we know is this, x plus h minus 1 over x plus h plus 1 minus f of x, which is this, x minus 1 over x plus 1 multiplied by 1 over h. And then we can combine. So this is the same thing as the limit as h approaches 0 of x plus 1, x plus h plus 1. Combine the denominators, and then x plus 1, x plus h minus 1, minus a bracket here, x minus 1, x plus h plus 1. Just to double check, and then we'll multiply it by 1 over h. So we did x plus 1, x plus h plus 1, x plus 1, x plus h minus 1, and then x minus 1, x plus h plus 1. And now we can say the limit as h approaches 0 is x squared plus xh, x squared plus xh minus x. So x squared plus xh minus x plus x minus, there is no minus here. Well, let's see. X squared plus hx, x squared plus hx minus x plus x plus h minus 1 minus, oh, and then we have to, you know what, I'm kind of messing this up here. X squared plus xh minus x, so x squared plus xh minus x plus x plus h minus 1 minus x squared plus hx, so x squared plus hx plus x, so x squared plus hx plus x minus x minus h minus 1, all over what we had before. One over h. So x squared plus xh minus x plus x plus h minus 1. So x squared plus xh minus x plus h minus 1 minus x squared minus hx minus x plus h plus 1 over everything we had before. This cancels out with this. This cancels out with this. This cancels out with this. Plus 1, negative 1 cancel. And it seems like we're left with xh minus hx plus h. We're left with plus 2h, it seems. So xh plus h minus hx plus h. Let's see if that's consistent. Seems like everything should cancel out with the exception of, well, we'll have to see. hx and minus xh are the same thing, right? So just 2h, so equals the limit as h approaches 0 of 2h over everything we had before multiplied by 1 over h. These cancel out, so we're left with the limit as h approaches 0 of 2 over x plus 1, so x plus 1, x plus h plus 1, x plus h plus 1. Right, which sort of matches here, except it's a -2 on their part. So we'll figure out why that is 2h, right? So this h and this h should be 2h, in my opinion. Yeah, it should definitely be 2h, so they made a mistake there. But this is your derivative, or, well, you would do 2 over x plus 1, and x plus h, which is x plus 0 plus 1, which is 2 over x plus 1, x plus 0 plus 1, which is 2 over x plus 1 squared. That's your derivative. And that would be your final answer. And they essentially left it off at this for some reason, but they could combine this. They didn't distribute their negatives properly, which is why they got a wrong answer. But this would essentially be your answer in this case. So 2 over x plus 1 squared, and that would essentially be your derivative here. We want to find the derivative using the limit definition. So remember that the limit definition of the derivative is the limit as h approaches 0 of f of x plus h, f of x plus h minus f of x over h. So your f of x plus h in this case is going to be 3x plus h minus 2. And then your f of x, we already know, is 3x minus 2. So this will be the limit as h approach. So f prime will be the limit as h approaches 0 of f of x plus h, which is just 3x plus h minus 2 minus f of x, which is 3x minus 2 over h, which equals the limit as h approaches 0 of 3x plus 3h, 3x plus 3h, minus 2 minus 3x plus 2 over h. These cancel out. These cancel out. We're left with the limit as h approaches 0 of 3h over h, which is just this. So the limit as h approaches 0 of 3 is 3 because the limit of a constant is a constant.